We've discussed planes in space, so let's do an example of how to find the equation of a plane given only 3 points. Well, I could draw this, but I'm not going to draw these points specifically. I'm just going to draw a generalized notion of what this would mean. If I had 3 points in space, I can always draw the vectors. So if I had points P, Q, and R, I can draw the vectors there. And then if I can think about those vectors just spreading out to infinity, I can just generate this huge plane. And then, since I have this generating vector PQ and I have this generating vector QR, I can always generate a normal vector using the cross product. So since we have 3 points, we can make 2 vectors, find a normal vector, and then use any one of these 3 points to define the equation of the plane. So if I call this P, Q, and R, then let's get PQ and let's get PR. So let's call V1 PQ, we'll call the directed line segment from P to Q, we'll call that V1. So that's going to be -1, +2, +3. And we'll do the directed line segment from P to R as -2, -1, and -4. So now we have 2 generating vectors. So once we have generating vectors, we can then find the normal vector. Okay, so we have to kind of go through here. We're going to get -8 I minus 6j plus k plus 4k plus 3I. So what is that? Minus 4j. So -5I minus 10j plus 5k. So at this point, you might want to do yourself a favor and just check that this is truly normal to that. So let's just do a quick check and say, all right, is v dot n actually equal to 0? Well, it's -5 times -1, so that's 5. -10 times 2, which is -20, and 5 times 3, which is 15, which is 0. So then what we have is, we know that v1 dot n is 0. Now we could check v2 dot n. You're welcome to do that. But anyway, we have at least a sanity check here that we've done this correctly. So then once we have that, we now have the normal vector and we have a point in space. So we can say the standard form is that where these are the components of the normal vector and these are the points in space. So the components of the normal vector, negative 5, x minus 3. If we pick p, I'm picking p as the point here, minus 10, x plus 1 plus 5, x minus 2 is equal to 0. And this would be a standard equation of the plane. Now, we also know that there are alternate equations for this plane. We could divide everything in here by negative 5 and we'd still have an equation of the plane. So we could say x minus 3 plus 2, x plus 1 minus x, or sorry, I'm so sorry. These are z's. This is also an equation of the plane because this would be working with a scaled version of the normal vector, but this would still describe the same plane. And we could also rewrite this. We could say x plus 2y minus z equals negative 1. So any of these are really equations of the plane because the normal vector is not a unique vector. We just generated one by using the cross product. All we need is a vector that's in the same direction as the normal. And so you could see this, or this, and know that they're all the same equation of the plane.